Welcome viewers to the next session on Galerkin weighted residual method. This is one of the important session of this course, finite element methods for beginner. In previous session we have introduced Galerkin weighted residual method and applied this method on fin problem, and in this particular session we will be applying Galerkin weighted residual method on 3D heat conduction problem. So let us begin with our session. So 3D heat conduction equation is given by this if we assume that the thermal conductivity is varying along x, y and z axis, and where Q is the internal heat generation. If we apply Galerkin weighted residual method, we get this equation for one particular element. We can write down this as delta over delta x. So if I apply Galerkin method, then we get this equation to be multiplied by the shape function as weight, where I is equal to 1, 2 up to n, where n is nodes per element. So it means there would be n number of equation. So if we take example of 8 noded element, just to explain this, if I consider a brick element, 3D element I have to take because I am dealing with the 3D equation of heat conduction. So if I assume that there are 8 node, or I consider the 8 noded brick element, then I can write down these equations as 8 equations as below. This is for first node and this is for node number 8, and this term I have written here separately after this plus sign, that q n1, and that is again for 8, and this is equal to 0. So this is how we can write down, and this will be rather analyzing for this equation because it is difficult to take along with all this set of equations, so we'll be dealing with this equation only. It means here t represents this, here in this equation t is equal to the approximate function that we have used. This is as n1 t1 and n2 t2 and up to n8 t8. We know I can write this in matrix form as t is equal to n1, n2 and n8 to be multiplied by this column vector of our nodal variable t1, t2 up to t8. And in short matrix form I can write this as n into t, where this n represents matrix and t here also represents matrix. So this is how I can write this element nodal variable approximate function as n t, where this n is represented by this and t is represented by this. So let me open this bracket and write my equation, that is the most general equation that we'll be using for further analysis. It is given by the elemental domain, that is del over del x kx del t over del x multiplied by ni d omega. So this is the term that it will be multiplied by all these terms. So we can write down the other component as well. So this is how I can write this complete equation. Now if you see this expression, this expression can be divided in two parts. One is the shape function, another is the heat part. We can solve it by integrating by parts. So these are my four parts of that equation that we have derived in our previous slide. So this plus this plus this plus this is equal to 0. So now let me solve this by parts, and when I integrate this I get the lower term. Then now if this is volume I get area integration, if it is area I get linear integration, if it is linear then I get constant value. So now it is volume integration, triple integration, I get boundary for this. So it is given by kx delta t over delta x multiplied by ni, and then it is on the boundary or the area, minus differentiation of first and integration of second. So we can write down here as k del t over del x. Here I can write k multiplied by the differentiation of the first, that is ni over nx, and then it is d omega. So similarly we can write down the other equations as follow. So second term we got like this, and third term we got like this. Fourth term we doesn't need to apply any by part differential integration, so that is why it remains as it is. Now let us substitute all these to get this form of the equation. It is, so if I substitute here I get this equation. So the boundary parts or the area component I have kept these together, and the volume component I have kept these together, and this is equal to 0. So we have the equation like the area, assuming this kx, ky, kz is same, so I can write down directly this k del t by del x ni d area integration plus this q component q ni d omega, that is equal to 0. Now we can focus on this, and this term I can write down this as qx, that is equal to minus k del t over del x. Qy I can write down this as minus k del t over del y. Qz I can write down minus k del t over del z. So these are the heat flux. So if I club all these three terms together, because at any case we have to give the boundary conditions on any element phase, so I can write down these terms together as it is minus q times qx nx plus qy ny plus qz and z, where nx, ny and z are the direction cosine of the heat flux vector, multiplied by ni d sigma for boundary minus k times, here I can represent this in matrix form as it is del ni over del x, del ni over del y, del ni over del z, and the vector del t over del x, del t over del y, del t over del z. Here, just to remind you that this Ni is for node number 1 to number of nodes on an element, and this T is nothing but it is NiTi. So that is what basically we should remember in writing these things, because you will be substituting this back into matrix form, and this is Ni d omega 0. These terms I can replace these as Qn is equal to Qx nx, that is the normal component to the surface Qn, and these are the components of this normal heat flux in x, y and z direction, or xy plane, yz plane and zx plane, ny plus qz nz, or in vector form we can write down this as dot product if I consider these as vector. So I can write down these in the dot product form, that is q dot n. We always specify heat flux along the positive normal direction of the surface, and that can be resolved in the components along all three planes. So either this heat flow can either be convective heat flow, or we can specify the heat at the boundary. So this particular term will have two components now. One is the heat convection component, and other is the heat that we specify on the boundary, how much heat is being taken away or how much heat is being given into the surface of the element. So this term I can write down in this form, that is it is minus boundary Ni Qn d omega sigma, that is equal to the two component, that is the one is the heat boundary condition, that we can specify the heat that in terms of q naught, heat flux on any boundary, that can be specified by this sigma, plus it, or it can be the convection term, that is h t minus t infinity, again on the boundary ni ni and this. So now I can replace this term with these two, because on boundary we will be having the heat flux boundary condition either in this form or in this form. So this is how we can replace this. So now next is to substitute these expressions into this, and we get final form of our equation as this q naught ni d sigma, plus I can open this and get this on boundary, that is h t ni d sigma minus, so this is minus, I should not have taken minus here, so it will be minus here, and it should be minus here, and this minus and this minus will become plus, so it should not be minus here, so I have to substitute with minus sign. So this minus and this minus will become plus, so I get this as h t infinity, that is the environment temperature is this. So now we have substituted here, instead of this we obtain these three terms, and then I can write down this term, that is integral on the element, that is k, and the matrix form ni del x, ni del y, ni del z, and then the temperature gradient del x, del t, del y, del t, del z, plus this q terms ni d omega is equal to 0. Now I will rearrange all these and write in a proper sequence, taking these temperature term together on one side, that this and this term, and all three terms on the other sides. I can write here, this is for the omega term, that is the element, k times del ni over del x, del ni over del y, del ni over del z, and then this temperature del t over del x, del t over del y, and del T over del Z multiplied by the domain, plus we can now write down the other term, that is because of the convective heat transfer. We can have this H times Ni. I can take even H outside, D on the boundary, and this is equal to minus integration of the element Q naught, that is the given heat flow on the boundary, Ni d sigma, plus again on the boundary, that is due to the convective heat transfer coefficient T infinity, that is the environment temperature, plus this is on the domain for internal heat generation. So now this is our main equation that we now can focus and try to expand in the form of finite element formulation. So let us take this first term, and if I take first term, I can remember my basic expression of field variable, that is how I have assumed my field variable for the case when I assume n is equal to 8, that is 8 noded brick element, and I can further write down this T as, or this in summation form we also use this from 1 I is equal to 1 to this Ti and I, and this I can write down in this form, that is n1 and 2 up to n8 and T1 T2 up to T8, or in matrix form we can directly write down this as n into T. So here these n and T are in matrix form, and similarly we can write this del T over del X as this del n1 over del X T1 plus del n2 over del X T2, and further del n8 over del X T8. And similarly I can write for del T over del Y, that is del n1 over del Y and up to del n8 over del Y T8, and the third term, that is del T over del Z, and this is equal to del n1. So I can write this expression in matrix form as, here we get del T over del X, del T over del Y, del T over del Z, and this is equal to some matrix, and finally we will be connecting these with the nodal temperature. So this is the size 8 into 1 and this is size 3 into 1. So here I should have size 3 into 8, that is clear from the expressions that we have derived in our previous slide. So I can write down here del n1 over del x, del n2 over del x, and so on del n8 over del x. Similarly for del n1 gradient with respect to y, the differentiation of the shape functions with respect to y, and then it is to be populated with the differentiation of with respect to shape functions with respect to z. And this matrix is a special matrix known as B matrix in finite element method. So this matrix is B matrix. We can also write the first part of that integral that was given by del n I del x del n I del y del n I del z. So these are again where I is from 1 to n, that is number of node per element. So and if we assume it is 8 noded element, then it will be n is equal I is equal to 1 to 8. And what I get if I substitute I is equal to 1 to 8, it is del n1 del x del n1 del y del n1 del z. So this is when I substitute I is equal to 1. When I substitute I is equal to 2, we get del n2 del x del n2 del y del n2 del z and up to 8. So I have to substitute up to 8. So I get del n8 over del x del n8 over del y del n8 over del z. And this is, if we see this matrix and this matrix, we can find that this matrix is transpose of this matrix. So this is matrix is called B transpose. So now from this these two expressions, I can write the first part of the equation that we have written in our previous slides, that was K B transpose B, and finally this complete thing is to be multiplied by this vector, that is t1 t2 up to t8, or this I can write down as K matrix multiplied by this T vector. So where K is the conduction matrix and it is evaluated over the element by this expression K B transpose B and d omega. How this is to be evaluated? This is further to be integrated using different techniques, and we will be using Gauss quadrature rule for integrating this, and that is when we consider the natural coordinate system for our nodes. So this is first part of that equation, that K we have obtained this. Now about the second part, if we remember, the second part was that is it was Ni H T and D sigma, that is the on boundary. So this can be written as Ni is for 8, and where I is from 1 to 8, and this T is to be replaced with N times T. So here I can write down this as Ni is nothing but it is the N transpose, because this if we remember, the T was given by N into T in matrix form, where N was nothing but N1 N2 up to N8, and this T was in matrix form T1 T2 up to T8, and this T is representing here, this is from 1 to 8. So now it means that we have to write down Ni. So here this, when we write this for 1 to 8 node, I will be having N1 HT, N2 HT, N3 HT and so on. So it means it is coming in the column. So this will be N transpose. So I will be writing here, this is N transpose H I can take it even outside, and this T is given by N into T. So it is N into T on the boundary. So I can further write it down as on the boundary H N transpose N D boundary, and this whole is to be with this. So coming here, I can write down this as equal to K H T, where this is again the thermal stiffness matrix due to convective term. So I represent this with KH. So now let us write down the other terms. The next term was minus Q times, that is the heat, that is heat flux on the boundary, and this I can write down similarly for this as Q naught N transpose D sigma, and we call it as RQ. That R represents the right hand side vector and Q represents the heat flux boundary condition. And the next term is minus Ni, H I can take here, T infinity D on the boundary. Here also it has to be on the boundary specified or given as boundary conditions. This will be equal to minus boundary H N transpose T infinity and D sigma, and this will be calling it as right hand side vector due to convective term. And similarly I can write down this Q term, that is internal heat generation d omega, and here this is also for the elemental domain, and this I can write down as Q N transpose d omega, and this is equal to RQ, that is heat generation, right hand side vector for heat generation. So all these integral are to be evaluated over the element. Gauss quadrature rule is the most common that is used in finite element method for evaluating these values. So finally, for heat conduction problem, I can write down my equation as K. I can use subscript C. Some books may use this, some books may use here K. Some may not even use any C for the conductive term, but every notation is valid. So this is to be multiplied by field variable vector. This is equal to RQ, that is heat flux boundary condition load vector, RH, that is convective boundary condition load vector, plus RQ, that is internal heat generation load vector. So sometimes all are available, sometimes maybe only one or two or three are available depending on the situation to situation. So this is the general solution of finite element, general solution of heat conduction equation in finite element, where I suppose K, you remember that Kc is equal to K times B transpose B d omega over the element. We have to evaluate this. KH is equal to, this is on the boundary because of the heat convective term. So it is N transpose N d sigma over the boundary. RQ, that is heat flux boundary condition, it is given by minus of Q naught N transpose d sigma, and RH is given as minus of H N transpose T infinity due to the heat convective boundary conditions, and RQ, that is the load vector due to internal heat generation, is given over the domain, that is Q N transpose and d omega over the element. So these are the element values. So we can write this superscript as E. Initially we are not using, but at this I can write for E. If I remove E here from the superscript, these are the global stiffness matrix. So if E is there, it is element equation, and when we do not have E, it is global equation or system equation. So that's all for the 3D heat conduction formulation using finite element Galerkin weighted residual method. Thank you all the viewers for attending the session. Thanks a lot.